Good afternoon, everybody, and welcome to this webinar, which is in the EURASIP series of webinars. My name is Mads Gasper Christensen. I'm a professor and head of department at Aalborg University in Denmark. And I'm also, for another 13 days, the chairman of the EURASIP ASMSP TAC. And it is in this capacity that I'm hosting this event here today. So today's webinar is entitled Automatic Pathological Speech Processing. And the speaker today is Ina Kodrasi. And let me briefly introduce Ina. So Ina received the Master Degree of Science in Communication Systems and Electronics from Jacobs University Bremen, Germany in 2010, and the PhD degree from the University of Oldenburg, Germany in 2015. From 2010 to 17, she was a research associate and postdoctoral researcher at the signal processing group of the University of Oldenburg, where she worked on multi-microphone deaggregation and noise reduction. Since December 2018, she has been with EDIAP Research Institute Switzerland, where she leads the signal processing for communication group. Her main research interests include signal processing, multi-channel processing, pathological speech processing, and machine learning. So welcome to Ina. So the schedule today is that Ina will now give her presentation for about 45 minutes, and then after that there'll be time for questions. So go ahead, Ina. Thank you.
Thanks a lot for the nice introduction, Mads. I'm very happy to get a chance today to talk to you about some of the research on automatic pathological speech processing that we have been doing at the Signal Processing for Communication group at EDIAP. And I'll get right into it with a few words on the speech production mechanism. Speech production is actually one of the most complex motor skills that humans can perform through the very fast and very coordinated actions of about 100 different muscles. In order to be able to produce the desired waveform, there is several stages that have to happen. There is a speech planning stage where the brain organizes the thoughts into sounds. There is a motor programming stage where the sounds are converted into motor commands that specify how the speech muscles should move. And finally, there is an articulatory motion phase where these commands that were previously defined are now executed, where the lungs, the vocal folds, and various articulators like the lips or the tongue move in order to produce the desired waveform. Since it's such a complex process, it's also prone to impairments that can occur at any of these different levels of the speech production mechanism. Independently, where these impairments occur, what happens is that the resulting waveform that the person produces is then impaired. And this impaired waveform is what I will be referring to as pathological speech throughout this presentation. There is various causes of pathological speech. For example, neurodegenerative disorders like Parkinson's disease, amyotrophic lateral sclerosis, or Alzheimer's disease result in impaired waveforms for the patients. And right now it's estimated that there is about 8.5 million people suffering from Parkinson's disease, about 200,000 globally suffering from ALS, and about 46 million people suffering from Alzheimer's and other forms of dementia. And because of increasing population numbers and because the global population is aging, the incidence of these disorders and therefore of pathological speech is predicted to increase a lot more in the next decades. Another cause of pathological speech is hearing loss, which is also quite widespread, with about 360 million people estimated globally to suffer from it. And the reason why hearing loss results in pathological speech is because hearing loss patients have an impaired auditory feedback loop, so they cannot correct themselves while speaking. Another reason is also head and neck cancers, for example, where it's estimated that about 650,000 new cases occur annually only in the United States. So as you can see, there is various reasons why pathological speech occurs, and all of them are widespread, and they are going to become even more widespread in the future. And this highlights our motivation to tackle pathological speech in our research. Just to give you an idea of how pathological speech sounds like, I'll play the following examples.
trouble, and that's a particularly bad combination.
Upon graduating, I moved back home, and my first acting gig was
So as it's hard to get feedback in such immediate, quick feedback in such a webinar setup, but I'm not sure how many of you could hear that in the second example that I played, there were some distortions in the way that the person was speaking, but I'm sure you could all hear that the last example, there was a severe intelligibility issue and the communicative ability of the patient was severely reduced because that person had severe amyotrophic lateral sclerosis and therefore quite noticeable speaking impairment. These are the kind of signals that we are dealing with, and they are challenging for two reasons. They are challenging in clinical practice, which is what I'll concentrate on in today's presentation, how we are tackling these challenges for clinicians, but they are also challenging for various speech technologies. Unfortunately, I don't have time today to discuss this part of the research that we are doing in handling pathological speech for speech technologies, but at the very end of the presentation, I have one slide just to give you an overview of other quite productive research avenues that are going on in this domain. So pathological speech in clinical practice is quite important because one needs to be able to diagnose it, of course, to tell whether a person is healthy or suffers from a certain speech disorder, because speech impairments could be one of the earliest signs of several neurodegenerative disorders, for example. And in addition, it's also important to be able to tell whether a person is suffering from disorder 1 or disorder 2, because that gives the clinician clues about the underlying neuropathology that is causing this disorder. Moreover, once a person is diagnosed accurately, clinicians also still need to monitor the way that the patient speaks in terms of speech quality and intelligibility, since these characteristics are important to assess how the disease is progressing, whether treatment is working, how speech therapy is helping, and so on. All this in clinical practice is done through auditory perceptual assessment, which means that a clinician sits in front of a patient or a potential patient and tries to detect by ear any perceptual signs of the speech disorder in the way that the patient speaks. This can be pretty hard, and to show that this is indeed a pretty hard task, we conducted with our project partners some time ago a perceptual classification study where we recorded 29 healthy speakers and 30 speakers suffering from Parkinson's disease and amyotrophic lateral sclerosis. And we recruited 20 clinicians. We played the sound files that we recorded to them, and we asked them to note down whether they thought that the sound file was coming from a healthy person or a person suffering from a certain disorder. What we got was an overall detection accuracy of about 70%, which highlights that this is a quite hard task. So in summary, auditory perceptual assessments are labor-intensive. It takes time to have the patient read various things and try to judge by ear how the patient is reading these things. They are subjective. We got a pretty low inter-rater agreement in the perceptual study that we conducted, often correlated with the level of expertise that the clinician had. And such assessments are also very hard when the speech impairment is still in its early stages, because of course the perceptual characteristics of the disorder are very mild, so it's even harder to detect them by ear. And this is what drives the motivation for our research. What we want to do is to support the auditory perceptual assessments of clinicians through automatic assessments, which in contrast to auditory perceptual assessments are efficient, they are objective. Hopefully, if you run the same thing twice, you should get the same result. And if they work well, they can also be used to diagnose a disorder in its early stages. To give you some examples today in the presentation, I will discuss one approach for estimating pathological speech intelligibility, because as I said before, this is one thing that clinicians try to monitor for disease progression. I will present an overview very briefly of the state of the field when it comes to automatic methods to detect the presence of a speech disorder. And in this context, I'll discuss two issues that are quite important when it comes to being able to deploy these approaches in practice. That is their noise robustness and their adversarial robustness. So starting with an approach to estimate intelligibility, when we first started working on this, we were analyzing databases of healthy speech signals and of pathological speech signals in terms of various characteristics. And what we noticed is that all pathological signals that we were analyzing had very atypical temporal envelope fluctuations that looked very different from the envelope fluctuations of healthy speakers, even when they were uttering, when everybody was uttering the same phonetic content. As someone who comes from an enhancement background, when I saw this atypical temporal envelope fluctuations, the thing that it reminded me of was that in speech enhancement, a rather successful intelligibility assessment measure is STOI, which is actually based on comparing temporal envelope differences between noisy and clean signals to be able to tell what is the intelligibility of the noisy signal by comparing it to the clean signal, which is assumed to be 100% intelligible. So what we wanted to do is to adapt the idea of STOI to estimate pathological speech intelligibility. In this context, the noisy signal is the pathological speech signal whose intelligibility we would like to evaluate. The clean signal, so the reference signal, is not as straightforward because when it comes to pathological speech intelligibility, you can compare it to any healthy utterance, which should be 100% intelligible. So we didn't have a single reference signal, but we had multiple reference signals from multiple healthy speakers uttering the same thing. And whereas in STOI, things are time aligned, because if you have clean speech and noise on top of it, of course, the two signals are aligned. But when we have an utterance uttered by two people, or even by the same person twice, things are not perfectly aligned. But we need to take care of that so that we don't compare apples and pears when we compute the temporal envelope differences. To take care of that, what we use is dynamic time warping. And to give you more details on how the approach works, I have this schematic here where we have an utterance from a patient that we want to evaluate the intelligibility of. What we do is we compute its 1/3 octave band time frequency analysis, just like in STOI. And now we have to compare this to a reference that is 100% intelligible. For this reason, we collect utterances from multiple healthy speakers. Here you see R healthy speakers who are saying the same thing. We compute the 1/3 octave band time frequency analysis of all these utterances. And of course, they are not time aligned, but we would like to have one template representation of 100% intelligible utterance. And for that, we use dynamic time warping to align these various healthy representations to get our desired template. Now we can compare our 100% intelligible template to the representation that we want to evaluate the intelligibility of, so the representation of the utterance from the patient. But again, they are not time aligned, so we need to use dynamic time warping to align them again. And finally, we can follow the same idea as in STOI and compute the spectral cross-correlation, slide it over across time, take the average, and consider that to be our intelligibility score. So this is how the approach works. And next, I'd like to show how that works in practice when we evaluated on pathological speech data sets. For this, we took two data sets of neurotypical speech, so from healthy speakers, as well as of pathological speech. Everybody is uttering the same thing. But what we had for the pathological speech signals are intelligibility scores from clinicians. This is what we consider to be the ground truth. We took two databases just to evaluate the language generalizability, both English and Dutch, and also various disorders. So for the English database, we had patients with cerebral palsy. And for the Dutch database, we had patients with hearing impairment. We also compared to various measures that had been used up until that point. that evaluated pathological speech intelligibility. We chose an I-vector-based and automatic speech recognition-based approach, as well as two features that were the voicing percentage and the range of fundamental frequency. And to compare these different measures, we used the Pearson and Spearman rank correlation coefficient between the ground truth scores that we obtained from the clinicians and the intelligibility scores that we obtained from these different measures. And the results are shown on this slide, where in this first column, you see the results for the English cerebral palsy patients. And in the second column, you see the results for the hearing impaired patients in Dutch. You have the Pearson and the Spearman rank correlation coefficient for the variance measures that we consider. There is some numbers missing here because the studies where these other measures were proposed didn't report these numbers. However, what you see is that overall, p-STOI gives considerably higher both Pearson and Spearman rank correlation coefficients, both for the English database as well as for the Dutch database. So it works well and it generalizes across languages and pathologies. Since we proposed p-STOI, we have developed other intelligibility measures that have other advantages in comparison to p-STOI, which I will not enumerate now. However, we never managed to beat the performance that we got from p-STOI. So it seems that p-STOI works pretty well, even in face of everything else that we have done since then. This is why I chose to present it today. This brings me to the next examples that I wanted to discuss, which were approaches to automatically detect the presence of pathological speech. And the state-of-the-art literature has taken various directions in this context. There is a lot of work that has been done using traditional machine learning-based approaches, where the idea is take a recording, extract handcrafted acoustic features that are hopefully motivated by domain knowledge from the clinicians, use these features as input to classical classifiers like a support vector machine or an MLP, and train that for pathological speech detection. There is a lot of features that have been used, like melt frequency capsular coefficients, sparsity, fundamental frequency, and so on and so forth. And there is promising results that have been obtained using such approaches. However, there is no guarantee that the handcrafted acoustic features that we are designing are truly showing this domain knowledge that we're getting from clinicians. Perhaps because sometimes this domain knowledge is not possible to be put exactly into equations and formulas that you can write down. And moreover, there is no guarantee that these acoustic features are actually capturing discriminant cues that perhaps we don't even know exist. Since we cannot capture this abstract discriminant cues, the world of state-of-the-art literature since then moved towards using deep learning as feature extractors. And in this context, a commonly used approach is to take a recording, chop it up into multiple segments. For each segment, compute the time frequency representation, like the short time Fourier transform, and then train a convolutional neural network, followed by some linear layers for the task of pathological speech detection. This sort of approaches outperform the traditional approaches that I was talking about before. But again, time frequency representations, although we like them because, I'm sorry about that. Although we like them because we have used them a lot and they're very useful in various applications to process various signals. Again, there is no guarantee that they exhibit the cues that we're looking for to discriminate between healthy and pathological speech. Since then, a lot of the literature is considering self-supervised models trained on very large number of audio files and speakers that have nothing to do with speech pathologists, but using them as feature extractors. And this slide here shows a representation of such methods where we take an utterance. We use a transformer-based feature extractor to extract features across time for this utterance. We combine these features across time more often than not just by taking a simple average and then we input this averaged features into a classifier like an MLP for training it for pathological speech detection. So these were the different categories of approaches that the field has taken for this task. And next, I would like to present you just a few numbers to show how they work. For this, I use a Spanish dataset of 50 healthy speakers and 50 patients suffering from Parkinson's disease, which is a relatively good database because it's age and gender balanced. So we get rid of any potential bias and confusing factors in our result. Since the data sets that we have in this field are quite limited, we followed a speaker-independent tenfold cross-validation procedure, which means we take 80% of speakers for training, 10% for testing, and the remaining 10% for validation, and we repeat this procedure 10 times. And what we report here is classification accuracy. So how well can we detect the presence of a pathology among the speakers with two approaches? The approaches I'm considering are the convolutional neural network-based approach that I just talked about before, together with this WOV2-VEC2 based approach, where a self-supervised feature extractor is used for the task of pathological speech detection. For the convolutional neural network approach, we get an accuracy of about 77%, and for the WOV2-VEC2 approach, we get an accuracy of about 83%. And not only based on these results, but also on other results that we have obtained that I will not talk about here today, we believe that these transformer-based approaches used as feature extractors outperform existing approaches like the CNN or the traditional machine learning approaches. And since then, we have optimized this performance even further. We have optimized our implementation, which layer we're extracting information on, and so forth. But these results are slightly higher now, but that's not important in this discussion today. The problem with these approaches, even though they show promising performance, is that this data set that we are considering here is recorded in an anechoic chamber. So the signals that we are dealing with, both in the training, validation, and test set, are perfectly clean. And this is not the reality. If we are to deploy these approaches in clinical practice, the clinical practice is not an anechoic chamber. So there is going to be noise present in the environment. And this is what I'd like to discuss next. That is the noise robustness of this automatic pathological speech detection approaches. The noise robustness issue in our application is twofold. On the one hand, we have a noise disparity, so a difference in the noise conditions in the training and testing data, which is an issue that's not relevant only for us, but many other machine learning-based applications that you can think of. There is always a domain shift between your training and testing conditions. I will present next an approach that we have recently proposed to resolve this domain shift in our application. But another noise issue that's probably applicable, I will not say only to our application, but to very few applications potentially, but it's really an issue for us, is that for existing databases, not for the one that I used before, but for other databases that have been used in the state-of-the-art literature, there is also a noise disparity between groups of speakers. So you have a data set that is containing recordings from healthy speakers and from pathological speakers. The healthy speakers are recorded in room 1. The pathological speakers are recorded in room 2. And when you train a classifier to discriminate between healthy and pathological speakers, you very likely end up learning to discriminate between room 1 and room 2 instead of what you really want to discriminate. So this is also something that we have proposed an approach to resolve recently, and I will discuss that afterwards as well. So what we propose to resolve the noise disparity between training and testing conditions is a test time adaptation framework, which is very simple, but it can be applicable to any model and any other classification tasks where this is an issue. And the idea is shown on this slide, and it contains several steps. We assume we are given some training data. We train our model on this training data, and now we have a test utterance that we want to infer our model on. We extract or estimate the noise that is present in this test utterance you can use various ways to do that. We follow the VAD-based approach, as you will see afterwards. And this estimated noise is then infused into a portion of our training data. So we add that to our training data. It doesn't matter whether the training data was clean or not. As it is, we add the noise that we have estimated from the test signal, and we use this portion of the training data to fine-tune the original model that we had trained. And this fine-tuned adapted model is then used to do inference on the test utterance. So how does this work in practice? For that, we use the clean speech dataset that you saw before, but now we also have a noise dataset, which in this case is coming from QUT noise with an SNR from 5 to 22.5 dB. We have the same evaluation procedure as before, speaker-independent tenfold cross-validation. We use classification accuracy to evaluate, and we apply our test time adaptation framework both to the CNN-based approach and the WOV2-VEC2 based approach to show that the framework is applicable to any model, actually. So in this slide here, you see the performance of the CNN and WOV2-VEC2 based approach in the presence of noise. In this case, the training data was clean, but the test data was noisy. On the x-axis, you see the SNR of the test data from 5 to 20 dB. And on the y-axis, you see the accuracy that you obtain when you don't do anything. You just use the model as you have it trained on your training data, which happens to be clean in this scenario. As you can see, as the SNR decreases, both the CNN-based approach and WOV2-VEC2 based approach are quite sensitive, and their accuracy drops considerably, with the accuracy being about 50%. So you might as well toss a coin with an SNR of 5 dB. When we incorporate the test time adaptation framework that I just talked about before, what we get for the various SNRs is a considerably better performance. We gain almost 10% in accuracy for the CNN-based approach and the WOV2-VEC2 based approach at the low SNR of 5 dB, and this gap closes as the SNR increases, which is to be expected, but the approach remains relevant even at higher SNRs. About the second framework that we have recently proposed to handle the noise disparity issue between the two groups of speakers. This is also applicable to any model and any classification tasks if databases that you have access to and that you are using in your research suffer from this issue. And the idea was to again use noise augmentation, to again use noise estimation, but in a different way. So in this case, we have healthy and pathological utterances that are denoted by YH and YP, as you see in equation 1, that are made of two components. There is the clean, healthy speech, the noise for the healthy utterance. There is the pathological speech and the noise for the pathological utterance. Now, the issue is training a model on this kind of utterances that you see here in equation 1 the model will tend to concentrate on the differences between NH and NP, if such differences exist, not on the differences between SH and SP, which is what you are actually interested in concentrating on. What we propose to do is to suppress these differences in the noise between the healthy and pathological utterances by adding an estimate of the noise present in one utterance to the other utterance with an appropriate scalar. And this is shown in equation 2 and 3. You see now the new healthy utterance is the old healthy utterance plus the noise appropriately scaled from the pathological utterance, an estimate of it. And the new pathological utterance is the old pathological utterance plus the noise from the healthy utterance, estimated and appropriately scaled. To make these two utterances in equations 2 and 3 look the same to a system in terms of the noise, you have to take care of the noise components to be the same in terms of their characteristics, but also of various SNR relations that are shown here in equation 4, but I will not get into details of. So in the end, to be able to implement such a framework, what we need is good noise estimates, as well as appropriate scalars, such that this system of equations here are satisfied. The assumptions that we made in our application is that the noise is relatively stationary, which is a reasonable assumption, and that the speech and noise are uncorrelated. However, the first assumption is not an assumption that you need for this approach to work. It's just an assumption that you need if you want to use a simple VAD to estimate the noise. But you can use more complex procedures to estimate the noise, and then you don't need the assumption about the stationarity of the noise. So, because the noise we assume to be stationary, we extracted noise estimates from the healthy and pathological utterances using a simple VAD and repeating the segments that we managed to extract through voice activity detector. We compute the scalars based on these assumptions that exactly satisfy the constraints that you saw on the slide before, based on the ratios and powers between the clean speech for the healthy utterance and the clean speech for the pathological utterance. And these powers were computed based on the powers of the utterances themselves, which can be directly computed, and the powers of the noises that we are estimating through the voice activity detection. So far, we have everything we need to implement the framework, and we test the framework on, again, the clean speech dataset that I used before, so the PC-GITA dataset. We use the demand dataset to introduce noise, but now, differently from before, the noise for each group of speakers is different in terms of its characteristics. Healthy speakers are mixed with noise type 1, pathological speakers are mixed with noise type 2, and the SNR is different. Healthy speech was mixed at an SNR of 20 dB, and pathological speech was mixed at an SNR of 40 dB. This choice of quite high SNRs was made to show that even when you think that the SNR is so high that it cannot make a difference, 20 dB and 40 dB for a system is very easy to recognize. Even though you wanted to recognize healthy versus pathological speech, it will recognize this 20 dB differences between the SNR. We follow the same evaluation procedure as before, speaker-independent tenfold cross-validation. We use classification accuracy, and we again consider both approaches to show that the framework is applicable to any model that you consider for your classification task. For implementing the procedure, we consider 3 different scenarios. We consider the standard training procedure. That means use the dataset as it is. You don't take care of the fact that healthy and pathological recordings are at different noise types and different SNRs. The second approach is use the proposed method, but assuming that you have a perfect estimate of the noise, because we want to assess how important a good noise estimate is. And the third approach is actually use the approach as we have it, as we propose it, by estimating everything. So this is what would happen in practice. And the results are shown on this table, and there is a lot of numbers, but let me try to unpack them one by one. So we have results for the CNN-based approach and results for the WOV2-VEC2-based approach here. We have results for the different implementation settings that I just explained, the standard one, the Oracle one, and the proposed method with estimated noise. And we have 2 test signals. We have noisy signals and clean signals. It's simulation. We have access to the noisy and the clean signals. In reality, you'd only have access to the noisy ones. But the reason why we include the clean ones is because if a model works well, ideally, you want it to have the same performance for pathological speech detection on clean signals as the performance you get on noisy signals, because you shouldn't learn anything about the noise. In practice, you'll probably get lower performance in the presence of noise than if you have only clean signals and your model is trained on clean signals. But that's something that we are not targeting here. Ideally, we want the same performance. If you don't take care of the noise disparity between the speakers and use the CNN-based approach, you get almost 100% accuracy for noisy signals, but 50% accuracy for clean signals. This means that the model is perfectly learning the difference between noise type 1 and noise type 2, or SNR1 and SNR2, but it's learning nothing about healthy versus pathological speech because it's not managing to extract any discriminative information when the noise is not present. You see the same result with WOV2-VEC2, almost 100%, almost 50% between noisy and clean test signals. When you implement the proposed method with Oracle noise, you get for both CNN-based and WOV2-VEC2-based approach, 70% performance in noisy scenario and 70% performance in the clean scenario. For the WOV2-VEC2, you get 79 and 80. So the performance for the noisy and clean test signals is very similar, which is exactly what we want. We don't want the method to extract any cues from the noisy signal that it cannot otherwise extract from the clean signal. However, when we use the proposed method with estimated noise, we still have a gap in performance between the noisy signals and the clean signals of about 8% here and 9% and 11% here, and 9% here, which we need to resolve by computing better noise estimates that what we have done in this work through the voice activity detector. So this were the two approaches and the two issues that I wanted to discuss with respect to the noise robustness issue in pathological speech detection. And this brings me to the last issue that I wanted to discuss when it comes to applying these methods in practice, that is adversarial robustness. Adversarial perturbations are actually imperceptible perturbations that can mislead models. So what I mean by that is, consider this example of utterance that you are plugging into your model to do healthy versus pathological speech detection. And the model decides that this utterance belongs to a healthy speaker. Now, somebody that has access to either parts of the model or some information, I will not get into details here, manages to add a perturbation to this original signal that is imperceptible. You can't see the perturbation if you look at it, even if this is not appropriately schematically depicted here, but imagine you can't see any difference between these two signals, and you definitely cannot hear a difference between these two signals. But this perturbation, even though it's imperceptible, it's enough to switch the decision of the model from healthy, that it decided based on the true signal, to pathological, that it decided based on this perturbation. This is quite bad when it comes especially to healthcare applications like pathological speech detection, because it's a severe security threat. But also, being able to craft such perturbations gives you insights into what the model is learning. If the model is concentrating on things that don't exist in the signal, and you introduce those things that are hidden because you can't hear them, then you should use this information to train better models, to train more robust models, not only adversarially more robust, but also in general for a better performance. So the question that we asked ourselves is, can we design adversarial perturbations to fool various pathological speech detection approaches? And I will not get into details of how we are designing these perturbations, but I would just like to present the results that we obtain, which is we design perturbations that are bounded by a certain SNR. And the SNR bounds you will see in the next slide. And that already gives you a feeling of whether these perturbations are perceptible or not. Because if the SNR is 100 dB, probably you won't be able to hear these perturbations. So again, we use the PC-GITA dataset. We use SNR bounds from 0 to 100 dB to generate our adversarial perturbations for each SNR independently. The same procedure to evaluate as before, a speaker-independent 10-fold cross-validation, and we use classification accuracy for each of these different SNR bounds in the presence of perturbations. Now, differently from before, we have an additional evaluation step to evaluate whether these perturbations are truly imperceptible or not. And for that, we chose to use speech enhancement objective measures like STOI, PESC, frequency-weighted segmental SNR, and capsular difference, which evaluates whether the adversarially perturbed signal is similar in whatever these measures are evaluating to the original clean, not perturbed signal. And we again considered both approaches, the CNN-based approach and the WOV2-VEC2-based approach, to show the generalizability of these perturbations. So the results we obtain are shown here. You see the SNR on the x-axis from 0 to 100 dB, meaning that at 0 dB, the power of the perturbation added to the original signal is the same as the original signal. You can you will hear that. And 100 dB is something that you will not hear. On the y-axis, you have the accuracy. The straight lines are the performance you get for the CNN-based approach and for the WOV2 VEC2-based approach when you are not trying to fool the system through adversarial perturbations. This is why they are straight lines independently of the SNR. The blue line is the accuracy of the CNN-based approach in the presence of perturbations, and the orange line is the accuracy of the WOV2 VEC2-based approach in the presence of perturbations. As you can see, already at an SNR of about 50 dB, which is pretty high, the accuracy of the system is, for both CNN and WOV2 VEC2-based approach, is 0%. I don't think we really need to look into detail at this measures of whether these perturbations are perceptible or not at 50 dB, because most likely they are not. However, here you see the results of STOI, PESC, capsular distance, and frequency-weighted segmental SNR for the perturbations that we introduced at different SNRs. And as you can see, at 50 dB, STOI is 1, which means that's the upper bound. So no difference really in intelligibility. The PESC is the maximum value in this implementation, which was 4.6. Capsular distance is almost 0, and the frequency-weighted segmental SNR is also at almost the higher bound in the implementation, which was 35 dB. So these results show that perturbations are actually not perceptible at an SNR of 50 dB, and we need to develop pathological speech detection approaches that are robust to these adversarial perturbations if we would like to deploy these approaches in a clinical practice. So in the context of pathological speech for clinical practice, these are the examples that I wanted to discuss today. I hope I gave a brief overview of speech intelligibility type of approaches, speech detection type of approaches, and two issues associated in this with these applications, the noise robustness and the adversarial robustness issue. But as I said at the beginning, I just wanted to briefly touch upon the issues that arise with speech technologies in the presence of pathological speech before I end this presentation. So the first thing I wanted to discuss is automatic speech recognition approaches, which have been traditionally developed and continue still to this day, although this field is becoming quite a wide field of research. They continue to be developed for healthy speakers, and when pathological speakers who do need access to such technologies definitely try to access speech recognition systems, their performance decreases considerably. So here you see an example of an automatic speech recognition system on healthy speakers and pathological speakers under the same utterances. So the phonetic content is exactly the same. And while the word error rate for healthy speakers is at 4%, for pathological speakers is at 40%. So we need robust automatic speech recognition systems for pathological speakers. Another example is speech enhancement. We have healthy speech and pathological speech emerged in exactly the same noise type at exactly the same SNR. And when we use a certain model to achieve noise reduction, we get a PESC score of 0.37 difference for healthy speaker. So delta PESC of 0.37 for healthy speakers, but almost half of it for pathological speakers, which is numbers that highlight the necessity to develop enhancement technologies that are applicable to pathological speech. And this is not everything. There is speech synthesis systems that don't work as well for pathological speakers as they work for healthy speakers. There is enhancement of intelligibility systems for pathological speakers, just to make sure that these speakers are intelligible to others. So you transform the signal in a way to improve intelligibility for others. There is privacy concerns for various speech technologies that have been researched considerably, keeping healthy speakers, healthy target speakers in mind, but not for pathological target speakers and more. So the takeaway from this slide is that speech technologies, a lot of them are traditionally developed for healthy speakers, and their performance deteriorates for pathological speakers, and we do need to make progress into developing technologies that work just as well for pathological speakers. And this brings me to the end of the presentation. Thank you very much for your attention. And I would like to thank the various collaborators from my group, as well as from various universities that made these results that I presented here today possible.
Thank you, Ina. Let's all give Ina a virtual hand. Let's see if we can find the right button here. There we go. Yeah, you're getting a lot of virtual hands now, Ina.
Thank you.
Awesome. Okay, so let's see if we have any questions from the audience. So we have one in writing here. How did you manage to isolate the issue of the different rooms used in the, what does it say? Used in recording the training data by looking at the results of the classification? It's about slide 23.
Slide 23. Do you mean how do we see these issues in these results, or do you mean how did we figure out that there was an issue in the first place? Yeah. The reason why we started looking into this is because every model that we developed, we tended to test it on different databases. And we always got certain improvements on the clean database, but on these other two databases that we used for this analysis, we got a very high performance all the time. It didn't matter what we did. We were almost at 99% classification accuracy all the time. So we felt that something must be wrong with these databases, or they were somehow databases with very easy pathological cues. And we couldn't really assess whether the databases had very easy pathological cues because we're not clinicians. So we tried to resolve to tackle the first issue. So we thought something is wrong with the database. And then we looked at the database, we computed the SNRs, we extracted only the noise part, we did some extraction of more characteristics, and we compared between the two groups of speakers. And then we figured out that this is actually what is happening.
We have another question here. Let me read it. Thank you for the clear presentation. I'm curious about the performance of p-stoy on the spontaneous, oh, excuse me. Sorry. Thank you for the clear presentation. I'm curious about the performance of p-stoy on the spontaneous speech and red speech in COPAS. If p-stoy performed differently for spontaneous speech and red speech.
I am. So we need reference template signals, right? So we need what we consider to be 100% intelligible version of whatever the patient is trying to utter, so that we can do a one-to-one comparison. To be able to generate that, well, it's easy for red text because you have patients and healthy speakers reading the same thing. So we have a version of that. But when it comes to spontaneous speech, you don't have 100% intelligible reference because you don't have a healthy speaker uttering whatever the patient uttered during their spontaneous speech task. So what we did for that is we used speech synthesis to generate multiple versions of whatever the patient said in this spontaneous speech mode, and used this synthesized samples as 100% intelligible reference signals. So using this approach, we did get a difference between the spontaneous speech task and the red text task in the performance of p-stoy, but I do not think that that difference is justified by the fact that you have different speech tasks. I think that difference is simply arising from generating the 100% intelligible reference through a speech synthesizer rather than through truly healthy speech, true speech signals, because this difference was very small.
Good. Okay, the questions are pouring in now. Let me see if I can read them before so no one pop up. How do you check whether there's an issue in articulation or prosody? Or how do you see first when you see the time domain signal of pathological speech?
I'm not really able to tell whether there is an issue in articulation or prosody or any other characteristic just by looking at the signal, whether in time or in time frequency domain. I'm not sure if clinicians perhaps that do this have more experience with visually pointing out regions where there are issues. But for us, it was always a matter of computing a lot more handcrafted acoustic features to try to evaluate these different dimensions that would reflect articulation issues or prosody issues. We'd calculate MFCCs for articulation issues and other measures for the prosody issues.
Thank you, Ina. Next question. I noticed the performance gap between Dutch COPAS and English UA speech when using PSTOI. I was wondering why there is such performance difference on Dutch and English pathological speech.
That's a very good question to which I don't have a very good answer. I don't know if there was inherently a difference between Dutch and English that would cause this difference and would make it harder for PSTOI to estimate the intelligibility, or if it's caused by the fact that the articulation deficiencies in one group were very different from the articulation deficiencies in the other group, because we had cerebral, this is a hard word, palsy patients for the English database and hearing impaired patients for the Dutch database. So it's completely different, the kind of
quite different
articulation
nature,
errors
yeah.
that they have.
Mhm.
So perhaps it could be because PSTOI, these temporal envelope differences are easier to capture intelligibility issues in one group of patients than the other. But that's something that we didn't really investigate further.
Mhm. All right, next question here. Thank you for the great talk. You verified that the network was learning the noise and not the speech and proposed a solution for that. Did you check if the same problem could happen to room impulse response? That is, the NN learned to classify the room instead of the speech?
Yeah, that's a very good question. We did, and it's true. It's very easy to learn room at recordings at a reverb time of 300 milliseconds from recordings at a reverb time of 800 milliseconds. So we are currently trying to adopt this same idea of equalizing this difference through introducing the same level of reverb in all recordings that you have. But one has to keep in mind that this is not really the best solution, because even for the approach that I presented before, we're doing noise augmentation. So what you're doing is you're ending up adding more noise to your data. So of course, it will make it harder to access the clues that you are interested in, because things are going to be hidden in noise. So if you add more reverb, it's also not ideal, because you're going to make it harder to access the healthy versus pathological clues that you are interested in. However, that's something that I didn't mention in the slides. That's the only idea we have come up with, that is add more noise or add more reverb to equalize these differences, because doing denoising or dereverberation is really not a solution, because you end up learning distortions caused by the denoiser or the dereverb approach that you use instead of the noise and reverb differences. So you cause changes in the signal if you follow denoising approaches or dereverberation approaches that are also easy to learn with a neural network, rather than the pathological and healthy cues that you are trying to learn.
Good, Ina. Thank you. Next question here. Thanks for this great overview, Ina. I'm still curious about the work regarding the adversarial attacks. Although you did not talk about the design of the attack, can you comment now a bit more on the design of these signals? That is, particular spectra, particular envelopes, other features.
Yeah, so the way we generate these attacks is actually projected gradient descent, but instead of following the normal procedure where you minimize the loss of the network to update the weights, what you do is you maximize the loss of the network to find the actual attack, because maximizing the loss means that the network will take the wrong decision. So the attack was designed in the time domain with no regard to how it looks, how it sounds, what comes out, nothing except for the SNR bound. But we did analyze the attacks that we generated like this, how they look like. And how they look like is, if you think of the PSD of the speech that goes like this, high at low frequencies and low at high frequencies, it was exactly the opposite for the adversarial attacks that we were designing. So the PSD would look like the other way. It would be low at low frequencies and high at high frequencies, which meant that this CNN-based and WOV2-VEC2-based approaches that we are training for pathological speech detection, they are actually learning features from the high-frequency components of our signals that they shouldn't be learning, because we are tricking them into making the wrong decision by introducing information in the higher frequency components. And that's something that shouldn't be possible. So if we want to develop more robust approaches, then we have to make sure that these approaches are not learning things from speech parts where there is no speech, actually.
All right. One final question here. Thank you for the nice presentation. Maybe I have missed this, but how did you determine whether speech was pathological or healthy based on the P-story score? That is threshold based.
We didn't actually predetermine that. So for the intelligibility estimation part, we assumed that we know whether the person is healthy or pathological. And the motivation was to estimate their intelligibility so that a clinician can use that tool to evaluate the progress of the speech pathology once that person is diagnosed, by evaluating how the intelligibility of this person is developing a long time.
Very good. Thank you, Ina. It looks like that was the last question. So let me once again say thank you, Ina, for the great talk. Thanks for volunteering to to do the webinar here. And thanks to everybody who attended here. I hope you all enjoyed Ina's talk. Well,
Yeah,
thanks so
thank
much.
you so much for the invitation, and thanks to everyone who was here today, and happy holidays, everybody.
Yeah, happy holidays. Take care.
Yeah, bye.
Bye-bye.